Hello everyone, welcome to the lecture number 31 of this NPTEL lecture series on charging infrastructure, and in this lecture we will discuss the further discussions on isolated DC-DC converters. In the recap, we have seen the forward converter and its operation. We have understood there are some limitations. For example, in this converter, since we have reset of the core, so we must provide this much time in which our core flux gets reset to 0 value. That's when we need to give sufficient 1 minus d Ts period. This also indicate we have limited duty ratio also, we can say. In other words, we can say we have also limited our switching frequency. We cannot go to higher frequencies, because if you are going for higher frequency, then my Ts will be smaller, and since my Ts will be smaller, my 1 minus dTs will be smaller. So my core flux may not get reset completely. So that is why it will limit the smaller value of Ts to which we can go, and that is when it will limit the switching frequency. Then in this case we have, since we have diodes and they are switching at every switching cycle, so that is why we have good amount of reverse recovery losses of the diode, and that will add to the overall losses of the power converter. Then if we see, since the flux in the core gets reset through this RF resistance, so we have the lossy reset of the transformer core, and that is when we also have another losses like I square RF losses across this resistance RF. And then we have also seen that since my flux is going from 0 to the maximum value and coming back to its initial value 0, it is not going in the negative direction. So the core utilization is limited nearly half. Why we are seeing core utilization is limited or half? Because we have V is equals to N delta B A times frequency of operation. Since my frequency, if we assume frequency constant A, my N constant, V constant, then in this case we are going from 0 to some Bmax value. Obviously this Bmax value is lesser than the maximum value which the core can go, maximum flux density value which the core can go. So since we could have gone to minus Bmax, negative value of B minimum to B maximum value, so we could have gone to minus Bmax value to plus Bmax value, and that is when we could have reduced the size of the core by half. Since we are going from 0 to Bmax value, we are actually use our only the half the core, or we can say that the area is kind of doubled in this case. So we can say that the core utilization is limited, which is nearly half. So for example, if we write, since here we go from 0 to Bmax value, so our area of core here is nothing but V by N Bmax value frequency. And if we would have gone, if the delta B would have been from plus Bmax to minus Bmax, then we could have written area of the core to be V by 2N Bmax F, because it goes from minus Bmax to plus Bmax. So that will give me my area of the core to be half, reduced by half. I mean, so that's why we are having the lower core utilization. We could have utilized the twice the core size, but in this particular converter we are just using half of the core. That is why core utilization is limited. And when the switch is off, it is actually blocking a good amount of voltages higher than the input voltage. So that is when this voltage rating of the switch is very much higher. Now one another forward converter configuration is there, which is forward converter configuration with demagnetizing winding. So forward converter with demagnetizing winding. Now in this converter, if you look very carefully, we have, instead of having single two windings, we have now three windings. Here the dot is here, the dot is here, and in this winding we have primary winding with NP turn, secondary winding with with NS turn, and the winding having the diode with the number of turns to be equal to ND. And if you look very carefully, in this case again the same thing will happen. We have DTS period, we have 1 minus DTS period. Now let us see what will happen in in, let us say this is Vp, here we have Vs coming over here. Now in this case, whenever my S1 switch is on in DTS period, the voltage across the primary winding is directly the V in voltage, which we have written down here. V in voltage, you can see here the V in voltage is here in DTS period, S1 is on. Because of V in voltage, we have here applied on this secondary side positive voltage Vs by Ns by Np times my V in voltage appeared over here, and because positive voltage appear over here, this diode is forward biased, and because this diode is forward biased, this diode will get reverse bias, and the current will be actually flowing through the inductor to the load. And if we do the KVL in this loop again during DTS period, the VL voltage is nothing but NV in minus V naught, same as that what we have seen in the previous versions of forward converter. And again these windings are, again all the three windings are wounded on the same core, so all the three are magnetically linked together. Now, so during this point, whenever I am applying the V in across this winding, at this place we are actually applying, we are applying positive negative. So we are actually applying not V in voltage, actually we are applying ND by NP V in voltage here. So because of that, this diode gets reverse bias, because we are applying some positive potential onto the cathode of this diode. So we have here this diode is reverse bias. Since we have reverse bias and we have only one winding, so the flux in the core will actually be rising linearly with the upward thing, because we have positive voltage applied with the slope nothing but equal to V in by Np. And if we see the voltage across DS1, whatever the voltage of DS1 we will get voltage across V in plus our voltage will be Nd by Np, which is applied across the DS1. So let us say this is with this polarity, so with VDS1, the voltage across this one is in this loop. If we do this in this loop, then it is minus and minus coming over here, Nd by Np into V in, which is coming over here. Now we will see, if we look very carefully, the ideal S1, this current, there is no current which is flowing through here. So that is why we can say this ideal S1 is equal to 0 we can say. So this is what we get in and since our switch is on, so this voltage across switch is 0. Now in 1 minus DTS period, since my S1 switch is open, what happens is that suddenly the current from here which is flowing over here was seeing the negative di dt. Because of this negative di dt, this polarity will get reversed. Because of this reverse, because this polarity is reversed, what happens is that this diode is reverse biased, and since this diode is reverse biased, the current IL current which is going over here has to find a pathway. It will find a pathway to D2, and that is when D2 is forward biased. And the voltage in 1 minus DTS period, the voltage across output inductor VL is nothing but minus V naught. And that is when we can ensure the volt second balance of this inductor, and that is when we will get the same value V naught is equals to N V in times D. However, if we look carefully how the other side converters look, I mean the third winding, which is the winding which is connected through the diode DS1, how it looks like. So since we are now having the negative polarity across this, so because of this negative polarity, we have in this way we have negative polarity which comes like this. Since we have comes like negative polarity like this, here also we have negative polarity, dot will become negative. Since the dot will get negative, this diode will get forward biased, and since this diode get forward biased, we have current drawn from the source in such a manner that the flux will be falling down. Because see, when we turn on this diode, in order to find the path in somewhere, there will be current which will be drawing in such a manner that we will be now applying the voltages in such a manner, we will have the current going from here to here, and the voltage applied across the core is nothing but minus V in voltage which will be applying, and that is when the flux which will be there is nothing but dying down with minus V in by ND voltage, because if the diode is forward biased, if this is now forward biased, so what happens, the V in will now apply across this winding ND, and since the dot polarity is such that the flux which have gone to some maximum value will be now falling down, because since all the windings are wounded on the same core, the flux in the core will now have the negative slope and it will now die down to 0 value, and it will die down with the slope minus V in by ND. Now since we are applying V in voltage over here in this direction, so what happens is that on this side we have Vs voltage which is applied in this direction to be nothing but equal to ND by Ns into Ns by Nd into V in, and on this side we have the voltage Vp to be nothing but equal to Np by Nd into V in. So if we do the KVL on this loop, what we have is, we have the voltage which will be appearing across Vs1 is nothing but V in plus Np by Nd into V in voltage appear across this switch, because in this one we have Vs1 to be equal to V in plus Np by Nd into V in this loop, KVL loop if we do, and that is what we have seen over here. And in the primary side we are now having a voltage minus V in Np by Nd applied over here, and that is when we will see our flux in the core gets die down with the slope minus V in by Nd. And since the diode is forward biased, we have nearly 0 voltage, or some negative forward voltage will be there, but that we assume to be nearly negligible, so it is 0. And since we are having the flux which is actually die down, so what we have is, we have now the current through the magnetizing branch will be dying down using the IDS1, and that will be nothing but Im which was there previously, because the current in this one will go to this. So Im is corresponds to this, Im is corresponds to phi m, that means the current required to magnetize the core of the transformer, which is, let us say, some peak value of current Im it is going. So that current will now be falling down, since here it was Im, it was flowing beforehand. So now what happens is that in this one, through this winding, it is actually nothing but this Im which will be sent onto that side, which is nothing but Np times Im divided by Nd, because we do Np times Im to be current which is going through the IDS1 times Nd, and that is what we have written over here. This is the value, this Im is nothing but this peak value what we have. It is not the slope, it is the peak value what we have, this Im times Np by Nd, where Im is the magnetizing, we can write Im magnetizing component of current, which actually led to phi m flux. So because flux is nothing but N times I, so if we have some I, so there will be some flux corresponds to this. So the Im is corresponding to that flux phi m is the maximum value of flux the core will go. So this is one interesting configuration forward converter, where we are actually resetting the core using another winding connected in this manner. Now here the disadvantage with this topology is, obviously we have a multi-winding transformer, so we have to wind one more transformer winding, we can say that multi-winding transformer. Second, obviously limited switching frequency, because we must ensure that this will die down to 0, this flux should die down to 0. We must provide some fixed amount of time during which this flux will die down to 0. So that is why we must have some sufficient 1 minus dTs period. So that is why we can say that we cannot increase our switching frequency beyond a certain point, otherwise the 1 minus dTs period will be very less. Now the third point what we will get is, now we have forgot to see one more thing. Since here negative positive is there, we are having Vn plus Np by Nd into Vn, and let us say the flux goes to 0 at this point. When the flux goes to 0 at this point, what happens is that this diode on the winding having Nd turns will now, which is connected across that, will now cease to conduct. Since it ceases to conduct, what happens is that there is no Vin voltage which will be applied across the winding. That is when there is a 0 voltage applied across this primary winding, and that is when the switch will now block only the Vin voltage across this, which is what we have seen over here. And voltage across this diode is also this Vin, because if you do this particular loop, it is the same Vin voltage which will be coming across this diode, and that diode is reverse bias, it is actually blocking the Vin voltage, the DS1 voltage. So that is what we will see, the Vin voltage VDS1 across VDS1. So we can reduce this number of ND turns to increase the slope, and that is when we can die it down to faster. In during that time we will increase our the voltage rating of the switch. So that is a trade off we have here. So what we can say that here again the switch S1 rating is greater than Vin input voltage. Again this is the thing. Fourth point, again since the flux is going from 0 to maximum and maximum to 0, so we can say that transformer is underutilized nearly half time, by half time. Half of this size transformer underutilized by nearly half times. And fifth point, we can say that here again one important thing which we did not discuss here is, whenever, see, every winding will have its own, we just remove this part, every winding will have its own leakage inductance, and this leakage inductance is not the inductance which is actually coupled with the other winding, it is the inductance which is associated with the same winding. So now the problem is, whenever you open this S1, some current which is flowing through here, IP current flowing through this primary winding, so some current is going through this winding. Now during this time what happens, suddenly you turn or open this S1 switch, so the things which is actually coupled will now actually move to the next winding. However, if we look very carefully, there is also the leakage component which is there, and that leakage component will actually generate, since we are negative di dt, we have negative L leakage times di by dt voltage which will be coming across this inductor, and that will have some peak value which you will see at the peak of this one, this junction, which is something like this, which looks something like this. Let me draw with red color. This will look something like this. At the initial period it will have something like this, that means the voltage will look something like this, then comes over here and then comes over here. This is my V in voltage, this is V in plus Np by Nd times V in, and this is the kick which will get, voltage kick which will get due to the leakage, L leakage dt, L leakage of this winding. So the fifth point which is associated with this configuration is only the voltage kick on, this we can say extra voltage, the voltage kick on switch S1 due to leakage inductance. So this is another disadvantage which is associated with this configuration of forward converter. Now, so this particular, this voltage kick also we can remove by using the dual switch forward converter, which is another configuration of forward converter. Let us see the dual switch forward converter. So in this particular converter what we have is, we have S1 switch we have diode connected over here, and then we have another diode, and then another switch, S2 switch, and this is nothing but winding, NP winding, NS winding, and on the secondary side again it's the same thing, CL, D1, D2, and this is nothing but diode, let us say DR1, and let us say DR2. So in this particular case, during DTS period, during DTS period, here again V in voltage is applied. During DTS period, S1 and S2 is on. So when it is on, the Vp what we are applying over here is the V in voltage. That's when here V in voltage will come, and the voltage across VL is nothing but the same NV in minus V naught, because this diode D1 is forward bias, this will be reverse bias, D2 will be reverse bias. And when we will turn off this S2 switch, what happens is that since the current direction is here, the current will be flowing in such a manner that it will actually keep on flowing in this direction, and this direction will be such that it will go here, then comes back to this place like this. And since these diodes are turned on, what we are doing is here we are applying minus V in voltage, because we are applying minus V in voltage here, and V in minus V in voltage over here. Here we are actually applying minus N V in across this secondary winding, and that's when this diode is reversed bias. Since this diode is reversed bias, the current which is flowing through is will be flowing through this, and we can say in 1 minus GTS period we can say S1 and S2 is off, and since it is off, we can say voltage applied through inductor is nothing but minus V naught. And if we do volt second balance across the inductor L, volt second across L, if we do, we will get nothing but V naught to be N V in, same thing, N V in times D, because it is following, it is having the same voltages across this inductance L in both the sides. So with this is also one way by which we can actually obtain the forward converter. And again here is the same thing we are having the flux going from 0 to phi m and then coming back to 0. And see here, if when the current goes down to 0, automatically this diode will be reverse biased, and that's when we have now applying 0 voltage from this primary winding, and that's when the flux will be going from 0 to phi m and then coming back to 0. So this is what, in this case it is going by V in by NP slope. In this case it is going by V in minus V in by NP slope. So this is this is DTS period, and this to this period, or if we, this is 1 minus DTS period, and after this point it is 0. Here again we must provide some 1 minus DTS period duration. So we have limited switching frequency, we have limited core utilization, same as what we have discussed in the previous configuration of forward converter. However, in this case the core reset is happening losslessly, and there is no voltage kick you will see across these devices S1 and S2 whenever the switches turns off. And here in this case the S1 and S2 switch is actually blocking, voltage rating is nothing but equal to V in. Here the voltage rating is same, but it uses two switches and two diodes in primary side, which are some of the disadvantages of this forward converter. And again we have limited switching frequency, we have reverse recovery losses due to D1 and D2. And the core utilization is half. All these disadvantages still persist with this configuration of forward converter. So now if you look, in case of forward converters, we are underutilizing our core as the flux density is going from 0 to positive maximum value, that means Bmax, and then comes to 0. We are not going in negative flux density region, that means in the third quadrant of BH loop. And if we could have made our flux density swing from plus Bmax to minus Bmax, then we can increase the core utilization. So let us see the converters which can make flux to go from its maximum value in the positive direction to its maximum value in the negative direction, and thus increasing the core utilization. So one such converter is push-pull converter, which we will see over here. So this is nothing but our push-pull based DC-DC converter. Now if you look in this particular push-pull converter, we have in this, instead of just using 2 winding, here we are using 4 winding, 2 on the primary side, 2 on the secondary side, and we are using the center tap to actually connect our different parts of the circuit. So here we have V in voltage which is connected in this manner, and we have D1 and D2 diodes which are connected on the other side in this particular manner. So let us see how this push-pull converter works. Here it uses 4 sets of winding, and obviously they are all wounded on the same core, and you can also make the center tap transformer as well. On primary side it has 2 NP turns, on the secondary side it has 2 NS number of turns. And here again the S1 and S2 switch can be IGBT with freewheeling diode or MOSFET with body diode. The diode represent the freewheeling diode or body diode if the switches are chosen as IGBT or MOSFET respectively. So let us see how this particular push-pull converter operates. Now if we look very carefully in the first period where we have taken just dTs by 2 period, in this period, which is I mean if I take from here to here, it is Ts by 2, and if I take, and this is another Ts by 2. So overall this from here to here it is Ts, that means from this point to this point it is Ts time period. Now if we look very carefully in dTs by 2 period, my S1 switch is on and my S2 switch is off, and D1 of this side is on. So that means my this switch is S1 is on. Since my, and now this switch what we are using, this switch S1 and S2 could be an IGBT, and putting the freewheeling diode across the IGBT, and or it could be a MOSFET which has body diode. In that case we do not have to put extra diode, already the diode will be there in the MOSFET. But for here in this case, let us assume that the switch, a very generic switch, S1 switch, now which comprises of both the switch as well as diode. If it is MOSFET, it will just be MOSFET with body diode. If it is with IGBT, it is just the IGBT, and we will connect a separate outside freewheeling diode. Now in DTS by 2 period, what happens is that this switch is on. This switch is on means this switches turns on. Now when this switches turns on, what happens is that there is positive V in voltage which will be applied across this winding, and it has 4 windings. So let us define this point A and B point. So since here there is a positive V in voltage applied across here because the switch is on, so in this loop already this dot is connected to positive terminal of V in, and non dot is connected to the ground, and that is when we will apply positive V in from this winding. As a result of it, since these all 4 windings are wounded on the same transformer core, so at that point at the top winding also we will have V in voltage which get induced. On the secondary side we have Ns by Np into V in voltage which get induced, and in fourth winding it is Ns by Np V in voltage which is get induced. Now because of this thing, since we have positive potential applied over here, this diode will get forward biased, while this, because the negative potential is applied to the anode of this diode will get reverse bias, and as a result of which we can say that D1 is on. Now since my D1 is on, what happens is that the current in this one will start, because the positive potential is applied across the winding, so current will start rising. Since the current is start rising, what happens is that there will be current which will be coming over here, and across VL we have voltage applied, nothing but Ns by Np. If we assume Ns by Np to be equal to N, so we can say it is N V in minus, from the other side minus V naught voltage, and this IL which is going over through this one is coming in this loop, flowing in this particular loop, and that is when we will see the voltage across the inductor is VL and V in minus V naught. And since our NV in is greater than V naught, we can say that the in IL current, the current which is going through this, the IL current, there is a positive rise in, there is a positive slope which is nothing but, you can say it is NV in minus V naught by L. The slope is rising slope. And if we look since the positive potential is applied, which is V in potential, so there is, let us say the flux starts from minus phi m value, there is a positive slope, and that slope is nothing but, and that means d phi by dt is nothing but V in by Np, and it goes until it reaches up till dTs by 2 period, it keeps on rising. And since D1 is the only which is conducting, so the current through D1 is nothing but equal to IL, so this IL will actually flowing through the D1, and since my D2 is reversed bias, so the D2 current is actually 0, and since I have turned on my S1 switch, this voltage across this is 0, and the current which is coming over here will get reflected onto the primary side or onto this bottom winding, and that current is also flowing through this switch. We define IS1 to be like this, it is N, it is nothing but NIL current which is flowing through switch S1, and that is how our system will work in this way during first dTs by 2, that means for half the switching period. Then comes the 1 minus dTs by 2 period, where what we will do is, we will, already my S2 switch was off, I will also turn off my S1 switch. That is when what we will see, from the primary side there are no voltages which are being imposed onto the winding, or which has been applied onto the winding, and what we will see is that whatever the current which is going through the inductor L, since this inductor L, the current has to find a pathway, so it will comes from here, it will comes from here. Since the windings are symmetrical, the current, this IL current which was there, will get distributed through ID1, current through ID1 and through ID2, and in that case both the D1, since in order to ensure the current is going like this, both the D1 and D2 gets forward bias, and since they get forward biased, the winding, both the windings on the secondary side, top and bottom winding, both get short circuited. That is when we can say that VAB voltage is equals to 0. Since my VAB voltage is equals to 0 here, since my VAB voltage is equals to 0, so d phi by dt is nothing but, sorry, n d phi by dt is nothing but equal to voltage applied, and since voltage applied is 0, so we can say d phi by dt is equals to 0. That is when we can say that there is no change in the flux during 1 minus dTs by 2 period, and whatever the value the flux was at, it will remain at that value. That is why we just make the straight line in the flux thing. Now here what happens is that this IL which is going over there gets distributed in between ID1 and ID2, and if we assume that the bottom part of the circuit and top part of the circuit is actually symmetrical to each other, so the current will actually get divided by half in both the diode D1 and D2. That is why we see this is the diode, this is nothing but, if we do here, it is IL current, this is nothing but IL by 2 current, and here also it is nothing but IL by 2 current in this period. And if we see very carefully, since my S1 switch is off, since it is off and there are no voltage which is applied from this winding, this entire V in is coming across this switch, and that has to block the voltage V in. And since there is no current flowing in the primary path, there is no current, which is 0 current through the IS1. So in this period, since my this part, this current, inductor current goes from the top winding and bottom winding, this V0 voltage is actually appearing across this inductor, and this, if you do the KVL in this loop, since these two are connected together, so that's why if you do the KVL loop here, what we will get is VL is nothing but equal to minus V0, because this minus terminal will come connect across across this point through this winding, and this will already connected here, so voltage across the inductor is nothing but equal to minus V0 if we do the KVL in this loop. So that's why we get the voltage minus V0 applied, and because since we have negative voltage applied over here, so here we will have minus V0 by L, through which the current is falling, and that is how we will get our entire operation of the circuit during 1 minus d Ts by 2 period. Now in next half of the cycle time, in next Ts by 2 period, so from here to here we are reached to Ts by 2 period. Now let us see in next dTs by 2 period, in next dTs by 2 period, what is the scenario. At that scenario, since we have already seen what will happen when just S1 is on and when both S1 and S2 is off, now let us turn on the S2 switch. So when you turn on the S2 switch, what happens is that across this winding we are applying negative minus V in voltage, because if this is on, S2 is on, in this loop the voltage which is coming over here is nothing but this negative terminal of V in is connected to the dot end, and positive is connected to the non-dot end, which was not the case in the previous dTs by 2 period, where our positive V in is connected to dot end and negative terminal of V in is connected to the non-dot end. Since that was the case, here in bottom also the same voltage gets induced, V in voltage, and on the secondary side we have dot will be negative, which is, we can say, Ns by Np into V in voltage will get applied. Here again negative and positive Ns by Np into V in voltage will get applied. Since the positive voltage which got induced is connected to the anode of D2, this diode D2 gets forward bias, and since it is a negative which is connected to the anode, this will get negative potential, so that's why this will get reverse bias. And because of this, what happens is that the voltage which is coming across the L is nothing but my, on one side it is Ns by Np, which is N V in minus V0. You can just do KVL in this loop. In this loop you can do minus this voltage minus Ns by Np V in plus VL and then plus V0, and that will actually, when you equal to 0, and that when you rearrange you will get this value. Now at that point the IL current which was there, since we know that our N V in is greater than V0, so we know that we have a positive slope which is shown over here, which is nothing but N V in minus V0 by L. And if you look very carefully, since we are applying a negative potential across this winding, so the flux in the core will actually falls down with a slope nothing but minus V in by Np. Slope it will fall down until the dTs by 2, second dTs by 2 period gets over, and during that point my D1 ID1 is 0. The current, whatever IL current is there, will be flowing through the ID2, that is why IL current is there. And since my S1 switch is off, so in this entire loop if we do this one, so we will get Vs1 to be equal to 2 V in voltage which will be coming across the switch, and that's what we will see, that we have this 2 V in potential coming over here across the Vs2. So that means Vs2 has to be sized for 2 V in potential, and the S1 is not conducting, the Is1 is equal to 0. Then comes the next state where we will have next 1 minus dTs by 2 period, this period where our S1 and S2 both are off, and this IL current was in this direction, and this is VL voltage. Okay, the current of IL is going like this, and since it is the same thing which we have seen in previous 1 minus dTs by 2 period, the current which is coming will get distributed in top winding and in the bottom winding, and because of that both the diodes get forward bias, because this current has to find a pathway, and that they will find the pathway only through these two paths only. And if we assume that this part of the circuit and this part of the circuit is symmetrical to each other, then we can say that our ID1 plus ID2 is equals to IL, and we can, since if we assume these two are symmetrical, we can say ideal 1 equal to ideal 2 equal to IL by 2. Now in this period what happens is that the again if you see the AB voltage is equals to 0. Since AB voltage is equals to 0, d phi by dt is equals to 0. That's why we have the constant minus phi m flux which is being applied in 1 minus dTs by 2 period. And since here in this loop, if we do the loop KVL in this loop, the across the VL we have voltage minus V naught which has been appearing. So that's why here it will fall down with a slope minus V naught by L. And since the ideal 1 and ideal 2 the equal current is getting flowed, the IL is getting distributed among ideal 1 and ideal 2, that's why here it is IL by 2, here it is IL by 2, and that's why we see that the average value of this is nothing but I naught by 2, and average value of this is nothing but I naught, where I naught is the current which is going into the load. The ripple will be going through the capacitor while the average value will be flowing through the load which is I naught. And during that time if you look very carefully, our Vs1 will be nothing but, since this is 0 voltage is there, so in this loop if you do this V in is coming across this S1, so that's why it is actually blocking S1 potential. And since the Vs there is no current going through the S1 switch, so it is 0, here our Vs1 is equals to V in. So we have seen in all the 4 period operation, what we see is that when we do the volt second balance of L, now what we realize it, we are actually applying N V in minus V naught dTs by 2 period, and then it is falling, the current will be falling down, so that means the flux has to fall to the same value. So in dTs by 2 period, so in the remaining the next period it is in 1 minus dTs by 2 period, and this 2 value has to be 0, then only the current will go to the same value, will come back to the same value, otherwise it will not be coming back to the same value, the IL current. That's why the IL current is like this. So the ripple part will be going through the capacitor, while the constant I naught current, which is the average value of this, will be going through the load, and this average value will only be changed if my load resistance changes. And in this the IL current goes from minimum value to maximum value and then comes back to the same minimum value in Ts by 2 period, and thus it repeats itself in Ts by 2 period. So we need to do the volt second balance in Ts by 2 period. So when we do this calculation, we will finally get V naught equal to N d V in, same as what we got in forward converter. Now if you look in the operation of this particular converter, there are two things which is quite different from the forward converter. Two things are, the flux here is now going from plus phi m to minus phi m, that means the flux density is going from plus Bmax to minus Bmax. That's when we can, if we do the V equal to N delta B AC into F, if we do that, so this delta B is going from plus Bmax to minus Bmax value, and that's when we will get AC to be nothing but equal to the area of core to be nothing but V by 2 N Bmax F, which was not the case in the previous condition where we were having V by N Bmax F, because previously the flux swing was from 0 to phi m, but here the flux swing is from minus phi m to plus phi m. So our core is fully utilized in this case, we can say. So that is the advantage we get. So we can say that advantage is of this converter is nothing but core is fully utilized. That means you have sized the core and you are using the full core. And here if you look very carefully, if you see in the L, the current going through the L, we have a current which has the frequency nothing but Ts by 2. So this inductor will see the current which is having the twice the switching frequency of this converter. That's when we have to filter out that twice the switching frequency component of IL current. That means the L and C has to be designed for twice the switching frequency, which was not the case in forward converter, where we have to size our L and C for entire Ts period. If we just recall our forward converter, we see our forward converter operation. Here if we see here, this one is entire for Ts duration, the ripple is there. So L has to be size for the entire Ts duration, that means for the LNC has to be size for a cutoff frequency of same as switching frequency. However, in case of push pull converter, we have understood that the inductor current has twice the switching frequency current, and that is when what we can say is that the cutoff frequency, we have to filter out that twice the switching frequency component of current in IL. So, the cutoff frequency, or you can say the frequency for which LNC has to be designed, is twice the 2 times of F switching frequency. Those are the advantages. However, there are certain disadvantages. Now, the disadvantage is obviously, the first point is the switch rating, the S1 and S2 ratings are doubled, that means they have to be sized for 2 times V in voltage. If you can see here, the voltage applied, maximum voltage applied in one Ts duration is nothing but 2 times V in. So, it has to block twice the voltage rating. And then the second thing which can occur because of the uneven voltage drop across these switches when they are conducting, there is a possibility of flux walking. That means the flux which has to come back to the same point, it will not exactly come back to the same point. Here we have written V in, so it will not be just V in, it is V in minus the voltage drop across the switch S1 when the S1 is on. So, that is the V in minus S1 switch here, and here it is V in minus the voltage drop across S2 switch at this place. So, here it is actually V in minus V S1 by NP. The non-ideal switches, the actual switches have some drop, and here it is our minus V in plus Vs2 by NP, and this Vs1 and Vs2 during when they are on, switches are on, are having different voltages due to the different manufacturing processes or different devices, and whenever they do production, it will always be having different values. Because of that thing, there are unequal voltages which will be coming across this winding, and that is when our this slope and this slope will not be same, and that is when we can say that there is some flux which will remain be there, and which will actually have something like this will happen. So, it is goes from here, goes here, goes there like this. In actual case it should be like this, but in real case it will be, let us say if it starts from the same point, it goes here and it will come back with a different slope. So, it reaches here, then it will come back here, it goes with the same slope here, goes up here, and then it will come up with different slope until this point, and then here it is, and then it goes. So, it is going in one direction. So, the flux, if we draw the flux with respect to time, it is going in one direction, and after some time this flux will keep on going, and it will reach to the saturation value of the flux, and that is when the core gets saturated, and that is when it will cease to perform, or it will stop performing as a transformer. And I mean, if you see in this way, because our, see, we have to come back to the same point, but it is not always coming back to the same point. It will have there is some DC shift which keeps on going, and after some time this will reach to this Bmax value, the flux will reach to the corresponds to the Bmax value, and that is when our core will get saturated. So, flux walking phenomenon which lead to core saturation after some time. So, you have to apply a certain method by which you can avoid this core saturation. This, one way is you can sense the transformer current or this current, you can sense this current, and accordingly you can slightly change the duty ratio to balance out that flux walking. And then the third thing, if you look very carefully, every coil has its own leakage inductance, and that leakage inductance, let us say when the switch S2 was conducting, there was current which is going through this, and suddenly in this case when the switch S2 is opened, So here there is some negative potential which will come across here, which is nothing but L leakage di by dt in the negative direction. The reason being why it is negative direction is, sorry, the potential, the current was flowing in this direction, sorry, the current was flowing in this direction through L leakage, and since you suddenly switch off this thing, so what we will get is we will get negative potential, because my di dt is negative as the current goes from non-zero to zero value, So that is why our L leakage di dt is become negative, and that will come across this switch by adding this V input plus this leakage will be coming across the switch, and the switch has to further size to the that voltage kick will come, and that is why your switch has to size for that particular voltages. So when we turn off, you will see that the switch will see the voltage something like this, which is L leakage di by dt when it goes from on to off at that point. Here we have drawn for Vs1, similarly for Vs2 it will also be the same thing. Now this is one of the disadvantage, that means we can write disadvantage as the voltage kick, or you can, why we say kick, because it's a very for applied for very small period of time. So voltage kick due to the sudden breaking of current through leakage inductance, and this leakage inductance, this voltage kick will appear on Vs1 and Vs2. The voltage kick you can say on S1 and S2 switch. So this has to be taken care while designing this converter. And another disadvantage are we have the 4 winding transformer is need to be wound. This is another disadvantage. So many windings of the transformer design will become quite complicated. So we have seen the operation of this push pull converter in this lecture. We will continue our discussion on going ahead with different converters like full bridge and all in the next lecture. Thank you.